Okay, so we're getting started on reactions of benzene, but first let's name a little bit of benzene stuff so that we can discuss what we're talking about a little more easily. Monosubstituted benzenes, a lot of them are named by naming the substituent and then benzene after it, like bromobenzene, chlorobenzene, nitrobenzene, ethylbenzene. Super creative, right? But some benzene derivatives have common names that are really pretty important and very commonly seen still now. This is toluene, aniline, phenol, benzoic acid, anisole, benzaldehyde, benzophenone. Common names that you unfortunately need to know. A couple more. That's benzonitrile, acetophenone, benzene sulfonic acid, and styrene. We actually talked about styrene previously when we talked about polymer chemistry. Yep. That's monosubstituted benzenes. A lot of them are named with the substituent and then benzene after it, or these common names that we just browse through super lightning fast. If you have a branch substituent that the benzene is hanging off of and you need to name this parent chain, you name the branched benzene as a phenyl group. Let me show you what I mean. Find the longest chain. That would be 6. Give the substituents the lowest number possible. That would be numbers 2 and 4. So it's a 2-phenyl. It's a 4-methyl. It's a hexane. And if you put that together alphabetically appropriately, 4-methyl 2-phenyl hexane. That's when you're naming benzene as a substituent hanging off of something. Okay, on to the real stuff. Reactions of benzene. Benzene typically does substitution rather than addition, and only when forced. That only when forced really means we're going to have some pretty strenuous conditions that we're subjecting benzene to. Yeah, only when forced. Okay. Aromatic compounds, such as benzene, undergo electrophilic aromatic substitution reactions. Electrophilic aromatic substitution reactions. It's a substitution, not an addition. That means benzene is going to be my nucleophile because it's going to react with an electrophile, and that electrophile takes the place of a hydrogen. It's an electrophilic aromatic substitution reaction. The benzene is the nucleophile that does the attacking. That terminology of calling this electrophilic aromatic substitution confuses many students. Benzene does electrophilic aromatic substitution. That means it's getting added to electrophiles. Benzene itself is the nucleophile. I know. Moving on. Oh, sorry. I meant to point out that you make a carbocation intermediate. We'll talk about these carbocation intermediates quite a bit. But these carbocation intermediates are extra special, extra special, because they always have resonance. This kind of intermediate, I'll go ahead and tell you the name, is sometimes referred to as a Wayland intermediate. That's the special kind of carbocation created when benzene acts as a nucleophile and attacks an electrophile. That special carbocation is called a Wayland. We'll talk more about it when we talk specifics of the reaction in a moment. Benzene is the nucleophile that reacts with some other sort of electrophile. When you do electrophilic aromatic substitution, you always end with an aromatic compound. If benzene reacted like a normal pi bond and did electrophilic addition, you would end with a compound that is not aromatic. This top compound is an addition product, not aromatic. The bottom compound, substitution product, aromatic. That's why benzene typically does substitution rather than addition, but only when forced. All right. Electrophilic aromatic substitution. There are 5 main electrophilic aromatic substitution mechanisms, and they all follow the same pattern. If you haven't figured out by now, organic is not about memorizing. It's about pattern recognition and being able to assimilate large volumes of information into digestible volumes of information. The first stage involves generation of a strong electrophile. Okay, here's my Y electrophile in my picture at the bottom. You got to make the electrophile first. Then benzene attacks said electrophile. Benzene attacks said electrophile. And it makes a Wayland intermediate. This guy is a Wayland. It's the special intermediate carbocation that's formed from benzene attacking an electrophile. And finally, some base in solution loses or plucks a hydrogen to restore aromaticity to your compound. 3 main steps in all of the electrophilic aromatic substitutions. We said there are 5 main electrophilic aromatic substitutions. Halogenation, you're going to stick a halogen on the benzene. Nitration, you're going to stick a nitro on the benzene. Sulfonation, you're going to stick a sulfonic acid on the benzene. Friedel-Crafts acylation, you're going to stick a carbonyl group on the benzene. Friedel-Crafts alkylation, you're going to stick a carbon group on the benzene. Yeah? The Big Five electrophilic aromatic substitution reactions. Let's see what we're in for. Electrophilic aromatic substitution starts with making an electrophile. And in this reaction, the electrophile is made by bromine attacking Feber. Feber, FeBr3, is a strong Lewis acid catalyst. What is a Lewis acid? An electron acceptor. That iron really wants electrons, and so bromine gives iron those electrons. It's a strong Lewis acid catalyst. Remember we said substitution rather than addition and only when forced? You guys don't recognize it really, but Feber, FeBr3, is a strong Lewis acid catalyst. It really needs those electrons. So, make an electrophile, done. Use benzene's pi electrons to attack said electrophile. So the blue part is making the electrophile. The purple part now is step 2, stage 2. Use benzene's pi electrons to attack said electrophile. We're attacking this terminal bromine and letting go of the bromine that has a positive charge. Attack the terminal, let go of the one that has a positive charge. What that gives me is a positive charge down here on this carbon where the pi bonds went away to attack bromine. That also leads to FeBr4 being in solution, where that iron in the middle is negatively charged, like so. This purple benzene-looking thing is a Wayland intermediate. A Wayland is a special type of carbocation that results from benzene attacking an electrophile. Wayland intermediates always have resonance. So if we draw the resonance of that Wayland intermediate, we're going to flip pi bond down that way. Remember, this corner is like the hinge on my door. That corner is uninvolved in the positive charge transfer. The positive gets up there because that one lost a pi bond. Swing that door, do-si-do, on around, positive, pi, bromine. These 3 resonance structures are of benzene. And remember, back in our resonance learning days, I said, if you compare those 3 resonance structures, which one might you say is the winner chicken dinner? Which one might you say is the one that contributes most to the hybrid, or are they all equal? You would say they're all equal resonance contributors. What are the rules for helping to decide resonance? I think I'm going to make that an Ed puzzle question. What are the rules for helping decide resonance? The number 1 rule is, you're going to tell me. And the number 2 rule is, you're going to tell me. Yep. That's what we're going to do. Okay, step number 1, make an electrophile. That's the blue part. Done. Step number 2, use benzene's pi electrons to attack said electrophile. That's the purple part. Done. Some base in solution, we're going to talk about who it is potentially, but some base in solution then grabs a hydrogen from the carbon that added the new group. That's super important. Where does the hydrogen come from? from the carbon that added the new group. Some base in solution grabs the hydrogen from the carbon that added the new group, and you dump in electrons to restore aromaticity. What's different about my product and the product up here that's given? The pi bonds are in different places. That's all. That's fine. They're the same molecule. It's a benzene. It's two different resonance forms of the same molecule. It's good. Every electrophilic aromatic substitution has three main steps. Make an electrophile. Attack said electrophile with benzene pi electrons. Lose a proton to restore aromaticity. That's our three different colors. That's our three different stages, three different phases. Electrophilic aromatic substitution, this is halogenation. Not so bad. I had to pause for a minute because I knew there was something else I wanted to say that I had forgotten to say. I said we would talk about who that base is. Fiber is a super strong Lewis acid catalyst. So while this is not a lot of protons floating around, this is very acidic conditions, this reaction. So when we say some base comes to clean up, this is a very weak base in solution. There are not a lot of things that could be basic in the solution. We will generally generalize, yes, I said that. We will generally generalize it and say B, some base. And I believe, I need to take another look at it, the textbook always says some general base like that. But what we could have drawn is that bromine is the base that comes to attack like so in this second green arrow I just added, this crazy long one. We could say bromine comes to attack like that because that's what generates my HBr as a side product up here. We don't really care about side products. We're real organic chemists, at least for the next few weeks. So we don't really care about HBr being created, but I'm pointing out how that HBr could be created because we said FeBr3 is a Lewis acid what? A catalyst. Catalysts are things that are not used up in the reaction. They're there in the beginning and they're there in the end in the exact same form. So Fiber was added as a catalyst, and Fiber is still there in the end as FeBr3. And the way that's regenerated as an FeBr3 is one of those bromides, goes and attacks the hydrogen to make HBr, regenerate your catalyst. Okay, that's halogenation. Nitration is another electrophilic aromatic substitution reaction. Step number 1 of electrophilic aromatic substitution reactions is generate an electrophile. Make an electrophile. This is the Lewis structure of nitric acid, and we do so many Lewis structures without drawing all those dots. Why did I decide to do them today? I don't know. We start out with nitric acid and sulfuric acid. Super concentrated nitric acid and sulfuric acid. It's like 16 molar nitric and 18 molar sulfuric. Yeah, it's really extreme conditions to have acids that strong all mixed together. When you do organic lab later, you'll get to mix together 16 molar and 18 molar nitric acid. Oh boy, it's a fun day for the professors. So we will take this lone pair from oxygen and protonate it. And you might say, why the heck would you do that? I know, I understand you saying, why the heck would you do that? Again, these are extreme conditions, and when I get to where I'm going to get to, maybe you'll understand why a bit better. On my nitric acid, I need to lose an OH from nitric acid in order to get an NO2 to add to my benzene. So OH, we just learned, is a terrible, horrible, no good, very bad leaving group. We could absolutely not eject hydroxide into this solution that is 16 molar and 18 molar sulfuric acid. You can't just let hydroxide leave. That's not allowed. 16 molar, 18 molar sulfuric and nitric acid. Let's find something to protonate. If I protonate the O that already has an H on it, that gives me a water, and that water can leave. I'm going to fold in electrons from my O minus and let water leave. The reason I fold in electrons from the oxygen at the same time is so that nitrogen keeps its octet. If I only lost water, nitrogen will be left without an octet, and that's not cool. So fold in electrons to keep nitrogen with an octet, and we get this thing. This thing, ta-da, is my electrophile. This electrophile has a name. The last electrophile didn't, but this electrophile has a name. His name is nitronium ion. Why because he's a nitrogen with a plus. He's a nitronium. Nitro with a plus. Nitronium ion. Step 1 of electrophilic aromatic substitution. Make an electrophile. Done. Step number 2 of electrophilic aromatic substitution. Use benzene's pi electrons to attack said electrophile. I did it. I reached all the way across the whole slide to do that. Use benzene's pi electrons to attack said electrophile. If benzene attacks that nitrogen, and I do no other arrows, that leads to nitrogen having more than an octet, and that ain't cool. That ain't even close to cool. So we got to fold some electrons up to one of the oxygens. It doesn't matter which. And from there, we get here. We'll put the nitro down there. Why not? And the positive in the corner down there. What kind of intermediate is this purple thing? It's a Wayland. Waylands always have resonance. And the resonance of this Wayland, we're going to leave the nitro alone. We're not going to resonate him. Could you? Sure. Do we want to? No. You don't even want to draw these that I'm drawing now. So there's one. Here's another. Nitrobenzene. Almost ready. There's my 3 Waylands. Make an electrophile. It's in blue. Attack said electrophile with benzene's pi electrons. It's in purple. Here's my 3 Wayland structures. Do I have any that's any more stable than any other? Do I have a winner, winner, chicken dinner, or are they all equal? They're all equal. All Waylands are not always equal. Be careful. These Waylands are all equal. After you attack said electrophile and resonate your Wayland, the final step is some base, somewhere in solution, plucks a hydrogen from the carbon that you just added the new group to. That's so important. And you dump in electrons to restore aromaticity and make your actual product. Yep. All right, since we spent a minute on it in the last one, who do you think the base might be in this reaction when we've got 18 molar and 16 molar nitric and sulfuric acid? Oh, yeah. It's going to be water, most likely. Where did the water come from? Well, when it's 18 molar and 16 molar, there are slight bits of water in there anyway. But water was my leaving group over there on that initial electrophile formation thing. Water is the strongest base that you've got in solution. Is water a good base at all? No, but water is the strongest base you've got in solution. Again, these are extreme conditions. We do not have very strong bases whatsoever, and you are perfectly fine with using B as in some base in solution. But I'm just telling you who that base might be. Back behind my scribbles, that says an alternate method uses BF4NO2. BF4NO2 is a salt. Oops, that's a BF4. BF4, the boron has a minus, and the NO2 has a plus. It's a salt, an ionic thing. All that is your electrophile is already formed. You don't have to go through all the blue steps. This is so chaotic looking, just taking a pause to look at it. You don't have to go through all the blue steps to get to the nitronium ion. The nitronium ion is already there. It's the cation in your salt that you use. That's all. All right, 2 down, 3 more to go. Sulfonation, step 1, make an electrophile. We're going to try to be consistent with our colors. And we have sulfuric acid. This is, again, super concentrated, like 18 molar sulfuric acid. Benzene does substitution rather than addition, and only when forced. So we're going to take 2 sulfuric acid molecules and react them with each other, like so, to end up with 1 sulfuric acid that has a water connected to it, kind of like that. That looks darn similar to that nitration mechanism we just did. We protonated one of the O's on sulfuric acid, but we protonated one of the O's that already had an H, with the reason being, let that water go. and we end up with an S with a plus. Whoops, whoops, whoops. An S with a plus. This also has resonance, and my brain was already thinking about that, and that's why I made that boo-boo. This has resonance that looks like this, where that oxygen has a plus. These two resonance contributors are of your electrophile. It's a sulfonium ion. Between these two resonance pictures, which one's the winner, winner, chicken dinner? Everybody's got an octet in both of them. In fact, sulfur is exceeding its octet, but he's a big old guy. He can handle that. The top one is actually the more stable resonance structure, the better, contributes more to the hybrid structure, because sulfur with a positive versus oxygen with a positive, sulfur is less electronegative, therefore it can handle the positive better. So, electrophilic aromatic substitution. Make an electrophile. Done in blue. Next, attack said electrophile with benzene's pi electrons. I'm going to attack the top resonance structure, but I could have just as easily attacked the bottom resonance structure. I just need to add an extra curved arrow if I do that. I'm not going to keep those arrows both on there because our slide gets crowded enough anyway, but I will keep them there until I finish drawing this structure, and then I will erase. This is a Wayland. Draw the resonance of the Wayland. I'm actually going to give myself a little more space. The resonance of the Wayland, there should be 3 of them. It's been a minute since you practiced resonance structures, I bet, but you got to get back in shape pretty quickly. Here's my Wayland. Anybody any better than any other, any winner, winner, chicken dinner kind of thing? Does one of these contribute more to a hybrid than any other? Nope. These are equal. So now I'm ready to, some base, somewhere, take a hydrogen from the carbon that you just added your new group to and dump in electrons. Who do you suppose that base might be in this reaction? Probably water, or water left from our sulfuric acid electrophile thing up top. But we can just make it a B, sure. This slide has a little note that says fuming sulfuric acid. What the heck is fuming sulfuric acid? Fuming sulfuric acid is SO3 mixed in with H2SO4. So fuming sulfuric acid, where do I have some room for it? We'll put it up top, I guess. Fuming sulfuric acid is SO3, that's SO with double bonds around the whole thing, and H2SO4 mixed. So in order to make the electrophile with fuming sulfuric acid, all you do is protonate one of those O's, and you get your electrophile. So the blue stuff gets exchanged for the orange stuff up in that top corner, and the rest of the mechanism is identical, because once you have your electrophile, you just attack it with benzene, and then you regenerate aromaticity. There we go. Whew. The Big Five says you can put on a halogen, you can put on a nitro, you can put on a sulfonic acid. It does not say, but you can also take off a sulfonic acid. So let's draw a reaction of desulfonation, taking off a sulfonic acid. So you start with your SO3H on there, benzene sulfonic acid. You add acid, water, heat. Sometimes that's called superheated steam. Weird, I know. And out of that, that's supposed to be a quote, out of that you get benzene. You take your sulfonic acid off. So this is also an electrophilic aromatic substitution thing. Your electrophile is your acid that you have already added to the mixture. There's nothing to do to make that electrophile. The electrophile is already there. It's acid. So you're going to need to use benzene's pi electrons to attack said electrophile. That should have been in purple if we're being consistent with our previous colors. Whoops. So out of that, we get a Wayland. This time, it's very important that you put the sulfonic acid on and that the hydrogen from the acid you just attacked gets connected to the very same carbon where your sulfonic acid is. And you got your plus next door. This is your Wayland. It's ready for resonance. Like this. You're drawing all these along with me, aren't you? I hope so. Hope I didn't just call you out right there. Okay, there's our Wayland. Is any more stable than any other? Nope, they're all equal. There really is a point to that question, I promise. We just haven't seen it yet, but there really is a point, I promise. So this time, instead of a hydrogen being lost to generate aromaticity, we're going to lose our sulfonic acid. Our sulfonic acid just falls off, and that hydrogen that we added from the beginning is in its place. You get some SO3H plus from where that sulfonic acid fell off. But again, sulfur is a big thing. It's got d orbitals. It does some strange reactions. It just gives up electrons and goes away. Yeah, desulfonation. Kind of weird, I know. All right, so that's 3 of our electrophilic aromatic substitution reactions down. Here's a 4th. And as I'm recording, I'm trying to decide if I want to stick this in with the same video where the other 3 have been covered, or if I want to start a new video all called Friedel Crafts. We'll see how it comes together in the editing room. I don't know. So Friedel Crafts, alkylation. Alkylation means adding an alkyl group to benzene. The way it starts, make an electrophile. AlCl3 is a strong Lewis acid catalyst. Why is it such a strong Lewis acid catalyst? You've got aluminum with very electronegative elements on it, like chlorine, and aluminum does not have an octet. It's a strong Lewis acid catalyst, just like Feber. So your alkyl halide, alkyl halide, that's what it's called, but I wanted to call it something else. Your alkyl halide, the halogen from your alkyl halide, attacks that Lewis acid. And you end up with this thing, aluminum with a minus and chlorine with a positive. Well, if you just let that chlorine go like that, you end up with chlorine without a positive. You get an AlCl4 with a minus on the aluminum, and you get a very familiar intermediate known as a carbocation. And carbocations are strong electrophiles. So carbocations are fantastic electrophiles for Friedel Crafts alkylation. We've shown one way to make a carbocation using an alkyl halide and a Lewis acid catalyst like aluminum trichloride. But in fact, any reaction that creates a carbocation can be, the carbocation can be the electrophile in an electrophilic aromatic substitution. This is one way an electrophile could be generated, but any reaction that makes a carbocation, that carbocation could be the electrophile in electrophilic aromatic substitution. Okay, make an electrophile. Done. Use benzene's pi electrons to attack said electrophile. Are you quoting me yet? There is a reason for my repetition, besides just making you bored. So we add our new carbon group, and we get a positive. This is a Wayland. And that Wayland, like all Waylands, has resonance. And while I continue to draw, maybe I can talk and draw at the same time. Are any of these Waylands any more stable than any other Wayland, or are they all equal? These Waylands are all equal. I promise there's a point to that question. We just haven't gotten there yet. Make an electrophile. Done. Use benzene's pi electrons to attack said electrophile. Some base in solution takes a hydrogen from the carbon where you just added your new stuff and restores aromaticity. Woo woo! I love it. Friedrichs alkylation. The carbocation is your electrophile. It could be any reaction that makes a carbocation. Oh, and actually, the some base, that's very likely a Cl minus that gets ejected from my AlCl4 minus. That's how that HCl is generated up here, just like the fiber in halogenation. Yeah, that's a Lewis acid catalyst. You end up with AlCl3 in the end, just like you started. I know we're skipping through this. We're going to come back to it, I promise. But we're skipping so that we can talk about the last of the Friedel-Crafts, the last of the electrophilic aromatic substitution, and that's Friedel-Crafts acylation, putting an acyl group on benzene. Step number 1, make an electrophile. All right, I've got AlCl3, that's a Lewis acid catalyst. I've got a Cl. Let's attack it, just like we did in the last thing. We get this. And chlorine can depart just like it did in the last thing. And this time we have a carbocation. But this carbocation has a special name. He's not any old carbocation. He's got a strange name. He's an acylium ion. Why is he an acylium ion? He's an acyl group. Acyl means COO group. He's an acyl group with a positive. Positive. An acylium has resonance itself that looks like this. Are either of those resonance pictures more important than any other? Does one contribute more to the hybrid than the other? Yes. I really kind of want to make you answer it. I absolutely think I should do that. The one with the double bond O contribute more to the hybrid. The one with the triple bond O contribute more to the hybrid. It's your turn to vote now. The one with the triple bond contributes more to the hybrid. Why? Because everybody has an octet. I write illegibly right there. Everybody has an octet in that Lewis structure. So, something that I did not make a big point of, because I'm just trying to get through all 5 mechanisms, something that I did not make a big point of is Friedel-Crafts alkylation, not acylation. Friedel-Crafts alkylation, the one we just finished, has a carbocation as the electrophile. And carbocations can shift. So sometimes you get weird products, unexpected products in Friedel-Crafts alkylation due to rearrangements of carbocations. But acylium ions, because they have resonance, that resonance is super stable. So acylium ions never, ever, ever rearrange. Never, ever. They don't do that. They don't rearrange. So you always get your acyl group directly connected to benzene, like in our product shown there. So, back to the business at hand. Make an electrophile. Done. In blue. It's an acylium ion. Benzene attacks said electrophile. You can attack either resonance picture of the acylium. It does not matter which one you attack. You're going to have an extra arrow if you attack the one with a triple bond, is all. So we'll put pi, carbon, double O, CH3 for the positive. This is our Wayland. All Waylands have resonance. Are any of these Waylands any more stable than any other Waylands? Ugh, I'm tired of that question. These are all equal. I'm certainly tired of that question when the answer is constantly, ugh, these are all equal. These Waylands are all equal, so I'm ready for some base in solution. Comes to take a hydrogen. We're going all the way up here because I'm running out of space. some base comes to take a hydrogen. Where does it take a hydrogen from? From the carbon, where you just added the new group. And you dump in electrons to make your product. Ta-da! Whew. 5, electrophilic aromatic substitution reactions. We will continue to talk about all of these in lots of detail. But that's a wrap for now. Peace out, yo.